We will now study a very important property of second order elliptic equations. So, these are called maximum principles. You might have come across this word already when studying complex analysis, and that's because the real and imaginary parts of an analytic functions satisfy are harmonic. Therefore, they satisfy Laplacian u equal to 0, and that is why you have maximum principles there also. So, throughout this section, we will assume that Aij 1 less than equal to Ij less than equal to n and A0 are in L infinity of omega. So, omega in Rn bounded open set and gamma is the boundary of omega. So, all these functions are the same and Aij satisfies the ellipticity condition. So, let me remind you of that. So, for every almost every x in omega and for every xi in Rn, so there exists an alpha positive such that for almost every x in omega and for every xi in Rn, sigma ij equals 1 to n of Aij of x, xi xij is greater than or equal to alpha times mod xi square. So, this is called the uniform ellipticity condition for these operators. Okay, so we have the following theorem. So, this is the running hypothesis. So, we have that let f belong to L2 of omega, u in H1 of omega intersection C of omega bar be such that integral on omega sigma ij equals 1 to n aij du by dxj du dv by dx I dx plus integral on omega a naught ub equal dx equals integral on omega fv dx. So, we are just giving that u in H1 of omega intersection C of omega bar satisfies a bilinear form AUV equals FV form. We are not saying anything about the boundary conditions of this function here. For every V in H1 0 of omega, then so this should be satisfied for every V in H1 0 of omega, because in the sense of distributions this means that the corresponding differential operator is equal to f, and because d omega is dense in H1 0 of omega. That is all that we are saying, and we are not saying anything about the boundary condition. So, that is why we have put this condition. Then the following hold. One, if f is greater than or equal to 0 in omega, u greater than or equal to 0 on gamma, then u is greater than or equal to 0 in omega. So, if you have f is non-negative, the data is non-negative and u is also non-negative on the boundary, then it also automatically satisfies this. 2, if a naught equal to 0 and f greater than or equal to 0 in omega, then u is greater than or equal to inf over gamma of u in omega. That means the minimum occurs on the boundary. Okay, the minimum does not occur. The minimum of the function is attained on the boundary. That is what we are saying. 3, if f equal to 0, a naught equal to 0 in omega, then inf of u on gamma is less than or equal to u is less than or equal to sup over gamma on u in omega. That means both the bound infimum and the supremum, the minimum and maximum of u, because it is a C of omega bar function, so it will attain a minimum and maximum, and that will be attained only on the boundary, I mean will be attained on the boundary, that is what we are saying. Okay, so the boundary holds the clue. Okay, so proof. So u is in h1 of omega, so this implies mod u, u plus, u minus are all in h1 of omega. We have seen this long ago in the, and even then I commented that this is the reason for maximum principles to hold. Okay, so then if u is greater than or equal to 0 on gamma, this means that u minus equal to 0 on gamma, because u equals u plus minus u minus, and u mod u equals u plus plus u minus, and therefore u equals mod u, since u is greater than or equal to 0. So u minus of 0 is in equals 0 on gamma. That means u minus belongs to h1 0 of omega. So we can use u minus as a test function in star. So we can put u equals, so we can set v equals u minus in star. Okay. So if you do this, and then you recall that u equals u plus minus u minus. Now what about the supports of u plus intersection support of u minus? Intersect only on the set. This is contained in fact it is contained in the set of all x such that ux equal to 0, okay, and on and u plus u minus vanish on the set, and du plus by dxi, du minus by dxi are equal to 0 almost everywhere on this set. So these are all properties which we prove. Whenever you have u equals constant, then you have u plus du by dxi, du minus by dxi there. Of course this set may be of measure 0, that is a different point, but then even if it is not of measure 0, this is always true. And therefore if you substitute, therefore you have integral ai sigma ij equals 1 to n aij du by dxi, du minus dxi dx plus a naught u minus dx equals integral omega f u minus dx. Okay. So now u is u plus u minus, and then u plus and u minus have that integral will be 0 because of all the observations which we have just now made, and therefore this will be equal to minus integral on omega sigma ij equals 1 to n aij du minus by dxj du minus by dxi dx minus a naught u minus square on omega dx equals integral omega f u minus dx. Now this f is non-negative, u minus is non-negative, so this integral is non-negative. A naught oh, I forgot to say that already. So this additional condition is a naught greater than or equal to 0 in omega. Okay, so these two conditions are necessary. Okay. So a naught is non-negative, u minus square is non-negative, so this integral is also non-negative, and by the ellipticity condition this integral is also non-negative. Therefore the left hand side is less than or equal to 0, LHS is less than or equal to 0, RHS is greater or equal to 0. So, the whole thing has to be 0. So, if that is 0, then each of the terms on the left hand side is equal to 0, and by the ellipticity condition. So, integral sigma aij du minus by dxj, this is 0, du minus by dxi dx, and that is greater or equal to some alpha times mod u minus 1 omega square. Okay, so mod u minus 1 omega square, then Poincaré implies that u minus equal to 0, and therefore this implies that u is greater or equal to 0. So, this is the very simple proof based on this sign arguments here. Okay, so we get the first thing. So, this proves 1. So, now for 2, let a naught be equal to 0. Okay. So, then if m is a constant real number, then u minus m also satisfies star. So, recall star. So, here this term has now disappeared, and therefore, you have Fv which has nothing to do with u. So, if you put u minus m, the derivative does not change, and therefore, u minus m is also a solution of star. Okay. So, now if you put m equals inf over gamma u, this implies that u minus m is greater or equal to 0 on gamma, and by 1 u minus m is greater or equal to 0 in omega. Three, if f is equal to 0 and a naught is also equal to 0, then you have, if capital M equals sup over gamma of u and small m equals inf over gamma of u, then you have m minus u and u minus m also satisfy star, and m minus u and u minus m are greater or equal to 0 on gamma, and therefore this implies that m is less than or equal to u less than or equal to capital M in omega. Okay, so this proves this theorem completely. So, this is called remark. Above result is called the weak maximum principle. You just have the sign of the data and sign of the solution on the boundary that determines the sign in the domain. Okay, so this is called the weak maximum principle. And so, remark, proof depends on the fact that u belongs to H1 implies u plus minus also are in H1, and therefore no such principle for fourth order equations, since such results not available in H2 of omega. So, this is purely a property of H1, and that is why second order equations have this nice property. Another remark, if a naught is greater or equal to 0 in omega, results of preceding theorem also true for integral on omega sigma ij equals 1 to n aij du by dxj dv by dxi plus sigma I equals 1 to n ai du by dxi v plus integral omega a naught uv equals integral omega fv for every v in h10 of omega. So, this is a slightly difficult thing. So, we refer to the book by Gilbarg and Trudinger. Okay. So, if u equal to 0 on gamma, then of course, it is both non-negative, non-positive, and f equal to 0 in omega, then we have both u and minus u are solutions, and this will prove by the previous theorem, since the maximum and minimum are both on the boundary, u equals 0 should occur on the boundary, and the boundary the value is 0. So, this implies u is identically 0 in omega. Okay. So, if you remember, we said that the solution of this will be a d-dimensional subspace, and the general equation will have when f is not equal to 0. So, when f equal to 0, the solution is a d-dimensional subspace of h1 of omega and h10 of omega, and the solution will exist for the general f only if it belongs to the orthogonal complement of another d-dimensional subspace in L2. But now this shows that if a naught equal to 0, that is, if a naught equal to 0, so solution for f equal to 0 is u equal to 0. Therefore, for every f in L2 of omega, double star has a solution. Okay, so by means of the maximum principle, we have, if you go back to the Dirichlet problem for this equation, we said that f should belong to the orthogonal complement of a d-dimensional subspace, where d is the dimension of the subspace of solutions when f equal to 0. And now that if f equal to 0, the maximum principle tells you that the solution is only u equal to 0, and that means d equal to 0, and therefore for all f you have a solution of the space. Now, the condition that u is in C of omega bar, that depends of course on the regularity theorems, which use the Sobolev embedding theorem.